Audio Jungle. Audio Jungle.
All right, so last class we had seen non-rotating cylinder, right? And as I mentioned, uh, circular cylinder, flow passed over circular cylinder, there was two types. That was non-rotating cylinder called NRC, non-rotating cylinder. Then we have rotating cylinder, which is nothing but RC. Okay. So last class we had seen that non-rotating cylinder. What is the important? As I mentioned many times, very important is what? Flow pattern. Okay. Then stream function and potential function. Then two velocity we have, radial velocity and tangential velocity. Then we'll have a stagnation point. Then we have Cp, which is called pressure coefficient. These are the important points you need to find. And we had seen all the points, yes, that last lecture, okay, which was non-rotating cylinder, and it is very important gate point of view, gate or any PSU exam, okay, one day exam. So this topic is very important. Same thing you have to calculate for the rotating cylinder also. Everything will be same. Same thing you will calculate here also, flow pattern, that is stream function and potential function, that radial velocity and tangential velocity, that is stagnation point SP, and pressure coefficient it was Cp. Okay. For non-rotating cylinder, you had seen that combination of the flow. What was the combination? Flow combination was, or flow, it was superimposed. What was that? Uniform flow plus doublet flow. For this also, we can say it is same. We have uniform flow plus doublet flow, and one more you have to add, it is vortex flow. Okay. So if you check till this combination, this two itself is what? NRC. In non-rotating cylinder, if you add vortex flow, so you will get what? Rotating cylinder. That is the job we have to do today. Okay. Hope it is very clear what we are going to do in this lecture. Now, so we'll give the heading rotating cylinder. Rotating cylinder or rotating circular cylinder, meaning will be same. Rotating circular cylinder. So what we have here? We have uniform flow, we have doublet flow plus vortex flow. Which vortex flow? Free vortex flow. Okay, it will give rotating cylinder. All right, or you can say this two itself, it is called uh, NRC, rotating cylinder. So you can add this three vertex. So what you will get? This rotating cylinder you will get. Right. Start now. So we'll draw the flow pattern first. So flow pattern I will show you. Flow pattern for rotating cylinder. In short, I will tell RC. So what are the combination? Uniform flow. This is the uniform flow. Plus this is what? Doublet flow. Okay. So and plus one more which is called vortex flow. Yes or no? Which is called vortex flow. Right. So we can add vortex flow. Vortex flow means, if I say vortex flow, it means it is a free vortex. Okay. So free vortex in the sense it is rotating about one point. It's a concentric circle. I explained what is the vortex flow. It's a concentric circle. Concentric circle means that a streamline will form circular. Streamline will form the circular form. Circular formation will be there. So obviously circle you may get, and all circle will have a same center. So it will be called concentric circle. All right. Now this is what? Free vortex. This is the point. Huh? What is the circulation for this? That will be gamma. Now here you may get the rotating cylinder, or for the rotating cylinder, one more thing you can say. What is that? This hole will be what? This hole will be NRC. Yes or no? So we can do one thing. We can draw the another diagram also if you want. What is the another diagram? We'll draw one circle. Like we know very well that non-rotating cylinder. This is what non-rotating cylinder. Now check here. This is the center. Okay. Non-rotating cylinder. First I will draw the axis. Now we'll draw circle part here. What happened? It's very difficult sometimes. Almost okay. So this is the center. Now if you draw non-rotating cylinder here and you show the flow, okay, this is what non-rotating cylinder. And for this circle you can say draw the hash line. It will be have like a solid surface. For this, what is the radius? It is capital R. All right, and directly you can say non-rotating cylinder plus this free vertex we have. Okay, free vertex we have here. Fine. Now this is what free vertex. So any two diagram you can draw. Okay. Now we'll draw the rotating cylinder. So in center I will draw, so it will be very easy to understand. This is the cylinder. Now it's rotating, right? Now it's a rotating case. Now it's a rotating case. What happening today? Okay, this is the cylinder. And now this today's whatever I am explaining, it is the rotating cylinder. So this cylinder will be having, because this is what one streamline, right? So it is rotating now. This cylinder is what rotating now. Yes or no? There is the rotation about the point, you can say it is rotating. The cylinder is what rotating. If it is rotating, so definitely that streamline will not go smooth like for this. See here, this streamline and this streamline is what uniform. Why? Because it is non-rotating. But if it is rotating, so definitely that streamline will be like this will be the streamline because it is rotating. So it will go like this. Draw properly. Okay. This will be the diagram. Because it is rotating cylinder. Okay. So the flow over the cylinder will also be a rotating condition because cylinder is what rotating. Now where is the stagnation point? Separate line I will show, so it will be more clear to you here. Okay. This will be the flow pattern for rotating cylinder. Remember, as usual for this cylinder also, radius will be R. Okay. And here I can show you that R and theta polar form so that it will be very easy to understand. Let me draw the separate color so it will be more clear. I can say This is what radius, this is what radius here, this is the radius of cylinder. I can say polar form, so this is small r and this is what theta. Okay, r and theta. This is nothing but, you can say, lifting flow over a cylinder. Over a cylinder. All right, lifting flow over a circular cylinder. Done. This is nothing but what it is called. It's called rotating cylinder or lifting flow over a circular cylinder. All right. Now for this, again I will draw the separate diagram. This is the axis. Here this is nothing but r, polar form. This is theta. For this cylinder, this is the capital R, which is the radius of the cylinder, and so just say this is cylinder is what we having a solid wall, and now the flow pattern will be like this only, as I mentioned. Okay, the flow pattern will be like this only. All right, here it is nothing but somewhere there will be the stagnation point, so I'm saying this is the stagnation point. Still we can find. Okay, we'll calculate that. This is the S1 stagnation point, this is the S2 stagnation point. All right, done. Now like in previous cases you have seen it, that all the steps. So this is the flow pattern, and this is basically, this is what, rotating cylinder. Why it is called rotating cylinder? Because vortex flow you have added. Earlier it was non-rotating, and now this is the gamma, which is called circulation. What is the gamma? Gamma called circulation. So if you give circulation, vortex flow means automatically circulation will come into picture. If you give the circulation, then flow will start rotating. Yes or no? So you will get the flow pattern like this. This rotating cylinder will have a lift force. Yes or no? Here you can check, here streamlines are very close to each other. If streamlines are very close to each other, then that area will be less, you can say. If area is less, velocity will be high. If velocity is high, then pressure will be less. So you can say here velocity is very high, pressure is very less. Okay, upper part I am saying, and that below part, here just opposite, velocity will be less and pressure will be high. So this will have the one concept of generation of lift force from high pressure to low pressure, lift generation. That's the reason it is also called, what it is called, it is called lifting cylinder. Lifting cylinder, or you can say lifting flow over a circular cylinder. Hope you understood. This is what lift force L, lift. All right, this one need to remember. It's very basic only. So here pressure is what, high, and here pressure is low, so it will try to push up the cylinder. Okay, that Magnus effect or swinging of the ball is basically that is the outcome of this concept rotating cylinder, no? Why there is the ball, cricket ball, why it will swing? Because if you throw the ball and if you rotate the ball at the same time, then it will swing. Why it is swinging? Because it is getting upthrust force or lift force, so it will not go straight, it will go in like a curve, you can say. Whenever that ball will fall on the ground, it will not go straight, it will go in some other direction, because it is having a rotation. So because of the rotation, it will have a upthrust force, so that ball may feel like a floating force, so it will turn the direction. All right, hope you understood. Magnus effect I will tell you later on. Anyway, so in very short, we'll go, this is the flow pattern basically. Okay, this is what flow pattern, this is the flow pattern. You should remember how many stagnation point you have here. We have a 2 stagnation point, and this 2 stagnation point will be changing. Okay, will be changing. There is the condition, it totally depends on the strength of this circulation. So once circulation will change, then definitely stagnation point will be changed. So here for non-rotating cylinder, this was the stagnation point, it was fixed. It was fixed S1 and S2 stagnation point. But here in this case, this stagnation point is what, not fixed. Okay, it is changing the position. This stagnation point will not be fixed. It is changing the position. Why? Because of this circulation. Because of this circulation, strength of circulation gamma, it depends on the gamma. Once gamma will be changed, definitely stagnation point will be changed. All right. So we'll see that. That is not a big issue. The thing is, you should know how many stagnation point we have. Question may ask. Okay, so for Rankine half body, there is only 1 stagnation point. Rankine full body, there is 2 stagnation point. Non-rotating cylinder, 2 stagnation point. Rotating cylinder also will have a 2 stagnation point. All right. Anyway, so now what is the next is what we'll go for the calculation of stream function and potential function. So we'll give a heading stream function. First we'll write stream function. Okay, what is the stream function? It is psi. Now so stream function for rotating cylinder, or also you can say, as I told you, it is also called lifting cylinder. In few books you may get lifting cylinder. Why there will be lifting cylinder? Because I told you, because of this variation of the pressure, you will have a thrust force which is called lift force, hence it is called lifting cylinder. Okay, now so for the rotating cylinder, what will be the stream function? So we can write stream function of rotating cylinder, okay, or lifting cylinder. RC means rotating cylinder. And how you got this? You got by the uniform flow, okay, plus you got by the doublet flow, okay, plus there is vortex flow. Also you can say, because you have a uniform plus doublet combination already, which is called NRC, non-rotating cylinder, so you can say psi NRC plus psi of vortex flow. So what is the psi of rotating cylinder? Psi of rotating cylinder is nothing but psi of NRC, non-rotating cylinder, plus psi of vortex flow. All right. What is the psi of non-rotating cylinder? That you should know. We already have derived in last lecture. Okay, so that formula you should remember. What was the psi? What was the psi? We'll see. Huh? Even I don't remember. So but you need to write it many times and you need to remember, because it is very important formula. Okay, and you cannot go for the derivation all time. Here for few like types of the flow, I explained the derivation. Actually it was not required, but just for understanding only I explained. but I will suggest all the formula you need to remember. Don't go for the derivation, it is not required. One time derivation is okay. Okay, you can understand by the book, with the help of book like Fundamental of Aerodynamics, John D. Anderson. From there only I am teaching. So Fundamental of Aerodynamics you can prefer, okay, for understanding. Or else you this elementary flow and all also you can follow RK Bansal, because few things I have taken from there also. Okay, so just for your understanding. All right, now just I will write the value of psi. Where is it? Wait. So psi is, I think, you sin theta 1 minus r square. You are sin theta 1 minus r square by small r square. Let me check this. You are sin theta, okay, 1 minus capital R square divided by small r square. Fine. So we'll write all this psi and phi. Already we know, directly we can. So you need to remember it, okay. The final thing is what you need to remember, because every time you cannot go for the derivation. So anyhow you need to remember it. So like Rankine, sorry, this non-rotating cylinder and rotating cylinder, as I told you today, if it is possible, we'll solve few gate problem also. So always remember, question they are asking from here only, okay. So now non-rotating cylinder psi will be what? It is nothing but u r sin theta, if you remember, 1 minus capital R square by small r square. What was the psi for vertex flow? I had explained in my lecture, okay. If you recall it, it was circulation upon 2 pi. Yes or no? It was circulation upon 2 pi ln r, okay. It was ln r. Or else if you go for the limit and all, simply you can write ln r also, that is enough, okay. If you apply the limit also, so from like small r to capital R, so you can write ln r divided by uh, capital R, or else you can write this one also, it is okay, no problem. So this is what the psi RC, okay. This is what psi RC, which is the stream function of rotating cylinder. All right, now remember this formula. Fine. Now we'll go for the potential function. Let me put in box. So it is very important, okay. It is very, very important. Fine. Okay, better I will write here only. What is the psi RC you got? It is nothing but u r sin theta 1 minus capital R small r square plus circulation upon 2 pi ln r. Now we'll go for the potential function at the same time. If it is possible to write potential function, which is nothing but phi. So what is the phi for rotating cylinder? Phi for NRC non-rotating cylinder plus phi for vortex flow. What is the phi for non-rotating cylinder? If you recall it, it was u r cos theta. Yes or no? U r cos theta, and in bracket it was 1 plus small capital R square by small r, and it was minus vertex flow circulation upon 2 pi theta. If I write this, recall it, okay. Sorry. Sorry. Now fine, this is what phi r. So if you remember only this final formula, that is more than enough. I mean, you can solve the problems, okay. This and this. Both are very important. Okay, now so stream function and potential function you have written. Now you will go for the velocity component. All right, we'll write velocity component. We can get that velocity. What we can find, you know, two velocity component you have, Vr and V theta. We calculate radial velocity, which is nothing but Vr. Okay, what will be Vr? If you recall the formula, what is the Vr in terms of stream function or in terms of potential function, anything? So what is the formula for the Vr? It is nothing but 1 upon r dou psi by dou theta. Yes or no? So you can write here 1 upon r dou by dou theta. Check what is the psi. Just now you have calculated. It is ur sin theta. It is 1 minus small capital R small r square, then plus circulation upon yes or no? Double parallel. You can calculate this. What you will get? Vr. So you can say RR cancel out. It will be what? Dou by dou theta. So it is nothing but RR cancel out. So U cos theta 1 minus, and this part will be 0 because if you differentiate with respect to the theta, so this part will be 0. Here sin theta will be cos theta, second part will be 0. So I can write like this. So what is the Vr? Vr is nothing but U cos theta 1 minus. Okay, this is the radial velocity. It's very important. Very important. Okay, what is the small r and what is the capital R? It should be very clear to you. It should be very clear to you, na? Suppose this is the cylinder. So for this cylinder, this radius is nothing but r, and any distance from the center, any distance from the center which will be the radial distance called small r. Capital R is the radius of the cylinder, or you can say circle. Okay, and it is at surface. At surface. Okay, so you can say at surface. What will be small r? It will be capital R. Yes or no? At surface, small r will be capital R. There should not be any doubt. What is the tangential velocity? Check. Tangential velocity. What is that? V theta. What is the formula of V theta? One, we have formula in terms of stream function differentiation with respect to radial, or you also have formula which is nothing but dou phi by dou theta 1 by r. Whatever is easy for you, you can do it. Both are correct, right? Tangential velocity will be what? Dou phi, means in terms of potential function dou phi by dou theta. To balance the unit, you just multiply by 1 by r. There should not be any confusion. Yes or no? So what is the tangential velocity? You just calculate. So you may get dou psi by dou r. No? I'm just taking first one. So minus dou by dou r. Stream function value we know. What is that? It is ur sin theta 1 minus, okay, check circulation plus circulation upon ln r. Yes or no? You just take minus outside, minus sign you take inside, so you differentiate. So you are sine theta, okay. So sine u and sine theta will be obviously constant. So two component you can say, this is the first one, this is the second one. So first derivation into second derivation minus second into first derivation, like that, no? So what you will do, or is you do one thing, you take this r is inside, so only one time you have to perform the derivation. So better I will take this, no? So it will be easier. U, we can say it is sine theta, and take r inside, so it will be easy to understand. Now fine, because r if you multiply inside the bracket, it will be small r into capital R square, and one r will be cancelled, okay. So only one denominator r will be there, fine, plus circulation upon 2 pi ln r. Now fine, now it is easier. Take minus inside, so you will have u sine theta, derivation will be 1, r derivation with respect to r will be 1, minus capital R square, 1 by r derivation is what, minus 1 by r square, so minus minus plus, alright, plus circulation upon 2 pi ln r. Circulation upon 2 pi ln r is nothing but 1 by r, it is circulation upon 2 pi r. Minus sign you are taking inside, so this will also be minus, sorry. So you need to remember this, okay. So put minus sign here. Now it's a fine. This is what tangential velocity. Hope you understood this. This is the tangential velocity. Now, so I can write this. We have radial velocity and tangential velocity. What is the tangential velocity you just achieved now? Minus u sine theta minus 1 plus minus circulation upon 2 pi r. What is the radial velocity you have achieved? Radial velocity is nothing but u cos theta u cos theta 1 minus, this is the value. If I say velocity, I can give the heading velocity at the surface of cylinder. So at the surface of cylinder, what will be small r? What will be small r? It will be capital R. Yes or no? Check. So what will be the radial velocity? Radial velocity will write first. Small r is capital R, then 1 minus capital R square by capital R square. So it will be cancelled out. Radial velocity will be 0. This is one outcome you should know, no? And what is the v theta? Check. It will be minus u sine theta, inside bracket it is 1 plus capital R square by small r will be capital R also, so capital R square by capital R square, cancel out 1 plus 1 2, so I can write 2u sine theta, okay, minus circulation upon 2 pi r. Okay, this is very important result here, okay. At the surface or on the surface of the cylinder anywhere, that radial velocity will be 0, okay, always remember this, and tangential velocity will be minus 2u sine theta minus circulation upon 2 pi r. All right. So we can get the next is like velocity we got, stream function, potential function we got. Yes or no? Now we are very interested about the stagnation point. Very interested about the stagnation point. So we will get it. So what is the next heading? It is nothing but stagnation points. Yes or no? How to get it? So it's very clear. We should have radial velocity 0, we should have tangential velocity 0. So this both, in the sense radial velocity will got Vr is equal to 0 when small r is equal to capital R. Just now you have seen, see this formula, when you will get Vr is equal to 0 directly when small r becomes capital R. So one is very clear. What about V theta? What is V theta? V theta is nothing but minus 2u sin theta minus circulation upon 2 pi r. You make it 0. So what you will get? You will get minus 2u sin theta is equal to circulation upon 2 pi r. What is the sin theta? Minus circulation upon 4 pi ur. Yes or no? So this is the value of sin theta. Stagnation point means what you are going to calculate? You are going to calculate r and theta. So what will be the theta here? Theta will be what? Sin inverse minus circulation upon 4 pi ur. Okay. This is the value of theta. Okay. Theta and r. So what is the r for the stagnation point? Small r become capital R. What is the theta? Theta, as I told you, stagnation point will change. For non-rotating cylinder, I told you stagnation point was fixed. If you remember, only starting only I said here only this S1, S2 and here. I said this is the non-rotating cylinder. So this is stagnation point here and here it is fixed. But I told you this stagnation point will not be fixed. Why? Because it will depends on the strength of source, gamma. Now check it. I hope now you got it. So see the theta value, which is the stagnation point, sin inverse circulation upon 4 pi ur. So if velocity uniform flow is constant, radius of the circle obviously it is constant, then gamma will be the main factor for the changing of theta. If gamma is changing, theta will be changing. Hope you understood. Yes or no? So I will write here next stagnation points. Which is nothing but r. So r you got theta, r you got small r is equal to capital R, and theta is what? Sin inverse minus circulation upon 4 pi ur, r theta. Yes or no? Very good. Now we will take cases, different cases, so you will get different theta. What is the case 1? Case 1 you can say, case 1 is if circulation is equal to 0. Check. So r is constant, r is not going to change, so I am not going to touch this. Only our concern is what? Theta. If gamma is what? 0, then what will be the theta? Check. theta will be sin inverse 0 upon what is the sin inverse 0? It may be sin inverse 0 when we will get when theta is what may be 0 or pi in a sense 180 degree, okay, radian value. Okay, two chances are there of the theta. When sin inverse 0 is what means what, maybe theta is what 0 or pi, because sin 0 will be 0 and sin pi will be also 0. So this is case 1. Now we'll go for case 2. Case 2. Okay, what is case 2? Check case 2. Now what is the case 2? I can say this gamma value, which is nothing but circulation, which is less than 4 pi RU and greater than 0. Okay, so what is the mean of it? That meaning is, if you calculate it, okay, if you calculate gamma is what greater than 0, if gamma is greater than 0, then what is the mean of it? I will tell you. Theta is nothing but sin inverse. I said if gamma is positive, so gamma is positive means already one minus is there. If gamma is, because gamma greater than 0 means what, gamma positive, divide by gamma is less than 4 pi RU. If gamma is less than 4 pi RU, okay, so definitely there will be one value, yes or no, and that value will be less than 1. Gamma is less than 4 pi RU means what, gamma is less than 1. So any value, sin inverse any value which is less than 1 will give any angle theta value, yes or no. Less than 1 means what, because minus sign is already there, gamma is greater than 0 and less than 4 pi RU means in bracket value will be negative because negative sign is already there. Okay, and gamma less than 4 pi RU means what, bracket value will be less than 1. So it may be minus 0.96, maybe minus 0.6, maybe minus 0.45, anything which is less than 1, minus 0.32, some anything. So it will give the value, and that value will be what, it will be the underneath the cylinder. Underneath the cylinder means anywhere we have, check, this is the cylinder. Okay, so underneath the cylinder means this is the upper part. Okay, this is the upper part, AB. So this is the above and this is the underneath the cylinder. Okay, so in this case, that value of stagnation point may be anywhere, maybe here, okay, 1 1, or maybe here, second case 2 2, like that, anywhere, or maybe here, but it will be underneath the cylinder. You can check the magnitude, you give the different value, you calculate the theta value, you may get, automatically you will understand. So anywhere, but obviously two stagnation point means one stagnation point will be here, another point may be here, or maybe another stagnation point will be at this point and this point, maybe another stagnation point, if you calculate, maybe one will be here and another will be here, anywhere, but two stagnation point you may get, and it will be underneath the cylinder. So I need to write here, in this case also you will have two stagnation point, but it is underneath the cylinder. What was the case? First case also there was two stagnation point. Here also there is two stagnation point. Okay, two stagnation point. Okay, one is at 0, another is at pi, just like a non-rotating. This gamma is what? 0 means what? It's a non-rotating cylinder. Gamma 0 means there is no vertex. If there is no vertex, it behave like a non-rotating cylinder. For non-rotating cylinder, where is the stagnation point? C. For non-rotating cylinder, where is the stagnation point? C. See here, it is theta is what? Suppose this is the theta. So one is at 0, theta is equal to 0. Another is at theta is equal to pi. If gamma is 0, it behave like a non-rotating cylinder. So mathematical calculation also you can verify it. It's very simple and very common calculation only, just like a previous. One thing I added, what is called vertex. So if you are considering gamma is 0, means there is no vertex. It behave like a non-rotating cylinder if gamma becomes 0. Second case, you are taking gamma greater than 0 and less than 4 pi RU. Again you will get two stagnation point, but it will be underneath the cylinder, means below side. Anywhere you can get, maybe in third and fourth coordinate you may get, but anywhere you can get two stagnation point. One in third coordinate, another will be in fourth coordinate. Okay. Now we will go for third case. What is the case third? We are taking circulation is equal to 4 pi RU. Check. So what will be the theta here? Theta is sine inverse minus circulation upon 4 pi RU. So what value you will get? Sine inverse minus of 1, because gamma you are taking exactly 4 pi RU. Yes or no? What gamma you are taking? Exactly 4 pi RU. So you will have sine minus inverse, sine inverse minus 1. Sine inverse minus 1 means what? What is the angle? It's I think sine 270. It's a sine 270. So what will be the theta here? 270 degree. One fixed value you got here. There is no another theta value. But was the previous case? Previous case you got 2 theta value. Here if you calculate, you will get 2 theta value. 2 theta value you may get. Okay, you can do by your own also. Calculation you have to perform by your own, you may get it. Okay. But what about here? Exactly minus 1, which means theta is 270. So where is the stagnation point for this? You can say this is the cylinder. This is what 0 degree, this is 90 degree, this is 180 degree, this is what 270. So where is the stagnation point? This is the stagnation point. Exactly at 270 degree. Okay, this will be the stagnation point for the cylinder. So how many stagnation point you have? One stagnation point. If I say stagnation point SP, so SP is nothing but R theta. You can say R, everywhere it is same, and angle is 270 degree. One stagnation point. We'll go for case 4. What is the case 4? If circulation 4 pi R, then what will be the theta? Sine inverse minus circulation upon 4 pi RU. If gamma is greater than 4 pi RU, then what is the mean of it? So one thing is very clear. If you solve that if you perform that calculation, okay, if you keep the value when gamma is greater than 4 pi RU. Okay, so gamma greater than 4 pi RU means in bracket it will be greater than 1. Okay, circulation value if it is greater than 4 pi RU. So in radius also, like in the formula what R value it was given, by that also you can calculate, or here also. So whatever the stagnation point you may get, it will, one stagnation point will be hypothetical. Okay, actually both stagnation point will be hypothetical, because if you go for the sign value, that will not be a greater than 1, doesn't matter plus or minus. Okay, maximum value is what, plus 1, or minimum value is what, minus 1. But here if you are getting theta sine inverse in bracket minus circulation upon 4 pi RU, and you are considering that case you are taking. Okay, circulation is greater than 4 pi RU. If it is circulation is greater than 4 pi RU, so definitely sine inverse bracket value will be greater than 1, so it becomes hypothetical, that is not possible. So but here also two stagnation point you may get, hypothetically you may get. One will be outside the cylinder, which is also hypothetical, and one will be inside the cylinder, which is also be a hypothetical. But if you check the flow pattern, so hypothetical in the sense mathematical point of view, if you check the flow pattern, so there will be one point inside the cylinder where the velocity goes to 0. Okay, if velocity goes to 0, so you can consider it becomes a stagnation point. Similarly, outside the cylinder also, if circulation is very high, means greater than 4 pi RU, then there also velocity goes to 0 at that point, at one point, and that point will also be a stagnation point. So it is the hypothetical basically, but calculation point of view, I will give the R value so that you can calculate. Okay, now here in terms of, if you check the R value for this case, so R value I will give to you. Okay, R value will be what, I will give the, like how to calculate it, circulation upon 4 pi RU plus minus Sridharachar d square minus 4AC. Okay, circulation upon, so this is the one derivation, but I will suggest don't go for derivation, it is not important. Okay, this is the R value. So plus minus if you do, then you will get it, but it is like if you go for the plus value, so you will go outside the cylinder. If you take minus sign, it will be inside the cylinder, and it is hypothetical actually. Okay, and theta will be, hypothetically you are taking theta value is what, 3 by 2 pi. Okay, fine. So where you will get it, it is very clear, theta will be 270, you are considering 270 degree. Okay, and where you will achieve it, it will be like if I will show the diagram, so diagram will be like this. Okay, when you are considering circulation greater than 4 pi RU, so where will be the stagnation point? So stagnation point will be here. Let me show here. This is the cylinder. Okay, this is the stagnation point. Sorry, cylinder. Now for this cylinder, if you want to check where is the stagnation point, so the stagnation point will be, one stagnation point will be here. Here, another stagnation point will be somewhere here. This R plus if you take, then you will get stagnation point here. So I can say this is S1 and this is what, S2. Okay, how that flow will looks like, the flow will be Okay. Okay, this is the center of the circle, this is R, and you are taking the case for the circulation gamma will be, which is nothing but gamma will be greater than 4 pi r. So if it is there, then this is what cylinder, and for this cylinder two stagnation point you have recognized where it is. One stagnation point will be here at this point, another stagnation point will be here at this point. Okay, so for all the cases we have seen the uh, all four cases, and that you need to remember. Okay, that you need to remember. Two stagnation point also you will have here. Two stagnation points. Okay, two stagnation points. One will be, you can write two stagnation points, one outside the cylinder, which is nothing but S1, and one inside the, which is nothing but S2. Yes or no? So this is the story, and how to calculate I have given the formula for R. Okay, so this is the coordinatic equation. Obviously if you solve R, well, two different value you may get, and one lies inside the cylinder, another lies outside the cylinder. Okay, by diagram you can understand. So now all whatever the story I have explained you. Okay, if you want to write the equation of a streamline for the circular cylinder, so that also you can do. Generally it is psi is equal to always 0. Okay, it's allowed the streamline, the centralized flow field that divides doublet flow and vertex flow. So one replace it is a solid body, and the circular cylinder and external flow will not feel the difference. The free stream can be considered as a vertex flow in that case. So these are the basic analysis for the circular cylinder, rotating cylinder you can say. Okay, and non-rotating cylinder also you have seen. All right. So just like a previous also non-rotating cylinder, you have seen the calculation for uh, what it is called pressure coefficient Cp. Similarly, we can calculate for this also.